Mba633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we will see how to use ANOVA to test for the equality of means for multiple populations, but this time we will not do any manual calculations. Rather, we will solve the problem using Excel only. The main objective here being to interpret the Excel output, Excel ANOVA output, and see how to use that to solve the hypothesis test problem. So the problem setting that we have here is the following. We want to see if a certain factor, in this case a diet additive, has any significant impact on the response variable, which is the blood glucose level measured in milligrams per deciliter. So actually this was a laboratory experiment conducted on rats. So in the first group you had 8 rats that were given the regular diet, so that's the control group. The second group of 8 rats were given a diet rich in fenugreek. The third group of rats were given a diet heavy in garlic, and the fourth group of rats were given a diet heavy in onion. Notice that there are 8 rats in each sample. I think 1, 2, 3, 4, 5, 6, 7, 8. Yes, 8 rats in each of the 4 samples. Okay, so the response variable, these numbers that you see here, are the blood glucose levels of these rats measured in milligrams per deciliter after they had been on this diet for about a week or so. And so there are 4 treatments over here, and these treatments are nominal. Do you see? There's one control group, one group which has fenugreek, another group has garlic, and for the last one has onion heavy diet. So our null hypothesis is that the mean glucose level for these 4 populations is the same. Mu C equals mu F equals mu G equals mu 0. So if the null hypothesis were true, then this factor, namely the diet additive, really has no significant impact on the blood glucose level. However, if we reject the null, then of course we are concluding that this factor, the diet additive, does in fact have a significant impact on the blood glucose level. So at least one of these diets, special diets, results in a significantly different glucose level. So here's the null and the alternate hypotheses about the population parameters, and we will choose between these two using ANOVA. So let's go to our Excel analysis. So we click on data from the menu tab, and let's see that the choices show up. So here I have data analysis, and notice I will choose single factor ANOVA since I'm trying to detect whether one particular factor, the diet additive, has any impact on the response variable. So I'll choose the single factor ANOVA, and first thing I choose is where is the input range. So here's my input data, and notice that I have included the labels in the heading also. So the data are grouped by columns, so the 4 groups are in 4 columns, and there are labels in the first row. Since we are doing a hypothesis test, we must also specify what is the tolerance for a type 1 error, namely the alpha, and the default in Excel is 5%, you know that. Now I have to specify where Excel should put out the output. So let's specify this particular cell H3 as the output and see what Excel provides us by way of an ANOVA output. So here we go with the ANOVA output. So let's see what this is giving us. As you can see, for each of the 4 groups, 4 populations here, control, fenugreek, garlic, and onion, the sample size is 8. There were 8 rats in each sample. Okay, so notice the average is 278.56, 224.16, 180.23, 271. Those are the sample means. You can see that they have been calculated here in red. They are the sample means, and I haven't shown you the calculation, but if you were to actually type in this data and calculate the variances for each of these 4 samples, these are the numbers you would get in that last column: the 225, 181.98, 291.03, 448.58. Those are the sample variances. Okay, so now let's look. The main output of the ANOVA is here, and this is what helps us either go with the null, not reject the null, or reject the null. Okay, So this first number here, 58122.31, this is the total sum of squares. Remember, SS stands for sum of squares, so this is the total sum of squares. Physically, what does total sum of square mean? It means the following. If we consider all 32 values, so these are the 32 values of blood glucose level for all 32 rats. If we think of this as one big group rather than 4 distinct groups, if you think of this as one big group, then the grand mean, the mean of these 32 values is 238.49. So if we take each data point, see how far it is from 238.49, square that difference and add them up. That is the sum of squares, total sum of squares. That comes to 58122.31. Okay. Now the within group sum of squares simply means treat each group separately. You remember doing these calculations manually when we did it for the previous video clip. So where do we get the 8031 from? Take each group and look at the mean for each group separately. So for instance, for the control group, the sample mean is 278.56. That's the blood glucose level. Take each data point and subtract it from the mean of its group. So take 288.1 and subtract it from 278.56, square that difference. Okay, so it's a squared value. Do the same for the second group, the third group, and the fourth group. The distinction, of course, here is that each data point is subtracted from the mean of its own group, not from the grand mean. Okay, so once you add up those squared values, you get what is within the within group sum of squares. That's the 8031. Okay, the between group sum of squares, where do we get that? You imagine that all 8 data points for the first group is concentrated at the mean of the first group. So all these 8 data points somehow got bunched into this middle. All the 8 data points for the second group are bunched at the mean for the second group. All 8 values for the third group are bunched at the middle, at the mean of the third group, and so forth. So each group is represented by its mean, and we are trying to see what is the difference of each group mean from the overall mean. So you take the difference of 278.56 minus 238.49, square that and multiply it by 8. Why 8? Because there are 8 data values, 8 values in the sample. Add this up for all 4 groups and you will get 50,090. So that's the between group sum of squares. Okay. Degrees of freedom, where does the 3 come from? The degrees of freedom for between groups is number of groups minus 1. Okay, so we have 4 groups, 4 minus 1 is 3, so there's where the 3 comes from. Where does the 31 come from? For the total, the degrees of freedom for the total sum of squares is simply the total number of observations minus 1. How many total observations do we have? We have 32 total observations. Okay, 32 minus 1 is 31. Degrees of freedom for within groups is total observations minus number of groups. We have 32 total observations and there are 4 groups, so 32 minus 4 is 28. That's where the 28 comes from. Okay, degrees of freedom. Now mean square, MS stands for mean square, is simply total, the mean square is simply sum of squares divided by degrees of freedom. So let's do the first one, sum of squares for between groups divided by 3, which is its degrees of freedom, and you see it's exactly 16696.9. Let's do the second one. It's the sum of squares for within groups divided by the degrees of freedom for within groups, and there you have it, 286. You remember what the physical interpretation of the 286 and the 16696 are. 286 is my estimate of the population variance, in this case the variance of blood glucose level, without assuming that the null is true. And 166.96 is my estimate of the same parameter, sigma squared, the population variance, but this time assuming that the null is true. So if the null were true, these two numbers should be fairly close to one another. Okay, but in this case I'm finding how different are they. You recall the way you compare and find out whether two variances are close to one another or not. is you take their ratio. So the F value that you see over here is just the ratio of MS between groups divided by the mean square within groups. So we are finding that the estimate of sigma squared, the population variance that I got, assuming that the null is true, is 58 times higher than the estimate of the population variance that I got without assuming that the null is true. That's quite a bit of difference, isn't it? So the next question we ask, how different is 58 from 1? I would expect this ratio to be 1 or something close to 1 if the null were true, but I'm finding a value that is way different from 1. I know that this 58 is highly unlikely, but let's see statistically how unlikely that is. So the way I would find that is simply by using the F distribution. Why? Because the ratio 16696 divided by 286, namely the 58 that we have, that number, that's an F ratio. So I use the F dist of 58.2. That's where I am on the x-axis for the F distribution. Degrees of freedom for the numerator is 3. Degrees of freedom for the denominator is 28, because that's how I got the 58, by dividing a numerator by a denominator, and I get the value 3 points. Do you see this is exactly the p-value over here? So remember the physical interpretation of the p-value, that is, if the null were true as an equality, in other words, if these two variances, the true variances, were actually equal, then what is the likelihood of getting an F ratio of 58.2 or higher? We are seeing that probability is 3.7 times 10 to the minus 12. It's practically close to zero. It's practically impossible. Okay, and if you recall, when we did the ANOVA, our alpha was 5%. So I'm willing to accept a 5% chance of making a type 1 error. And what this p-value is telling us is that based on what I see in the sample, if I do choose to reject the null, there is only a 3.7 times 10 to the minus 12 probability of making a type 1 error. That's practically close to zero. So I very comfortably reject the null in this case. Now, if we use the other method of doing hypothesis testing, namely the critical value method, the F critical says, well, you are willing to accept a 5% chance of making a type 1 error. So what F ratio would you consider high enough to reject the null? So I use an F inverse. I'm willing to accept a 5% chance of making the wrong call. My numerator degrees of freedom is 3 and my denominator degrees of freedom is 28, and we get 2.946685. So this is telling us that if I'm willing to accept a 5% chance of making a type 1 error, any F ratio that is greater than 2.94, I will say that it's highly unlikely that I would have gotten it by chance. And in this case, what I actually got is a ratio of 58 that is way greater than 2.94. So F is greater than F critical, so I reject the null. So this was my null hypothesis. I reject the null. Similarly, if I go with the p-value method, then the p-value is way lower than alpha, which is 5%. So I again end up rejecting the null. So this is how you go about interpreting the ANOVA output. Make sure you know exactly how each of these numbers in the ANOVA output, how they are computed, how one is derived from another, and the physical interpretation of the F value, the physical interpretation of the mean squared values for these two, the physical interpretation of the p-value, and the critical F value. So not only must you be comfortable with the arithmetic, but also the interpretation of the numbers that come out from the ANOVA analysis.